Evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to my latest video, my latest training video. We're really going to delve tonight in the training series into severe weather fundamentals part 2, and I'll show you the overview here in a moment. But we're going to cover everything from severe downslope windstorms to snow to freezing precip events, and right on down to even icing and turbulence. So let's get right into tonight's training video. Starting with the overview, you kind of see what we got going on here for the overview of the training for the video this evening. I'm going to cover downslope windstorms. We'll then move into heavy rain events. We got to think more than just the freezing precip and snow events. We also have the heavy rain events with flooding. Then we'll talk about the heavy snow events, the freezing precipitation events, and then we'll end tonight's training on the topics of icing as well as turbulence. All right, so let's first start the topic and the training off, this topic off with downslope windstorm types. And there's 3 types that we'll go ahead and cover in tonight's training. We'll talk about fall winds, we'll talk about Chinook winds, and then we will talk about Bora winds. All right, so with downslope windstorm events, when we talk about fall winds, these are winds that generally will come down higher elevation. And that's why we term them fall winds, because they're descending from that higher elevation. Katabatic winds, this is an example of a fall wind, and these can rush down elevated slopes of a mountain in excess of 100 knots. So these are some serious winds. You have very cold and dense air up at the higher elevations, and then it just races down slope. And yeah, you get some crazy wind speeds with these type of fall wind events. Winds originate when the cold air, again, is situated over a plateau or a highland area. You can even get these over ice sheets over Greenland or over Antarctica. That very cold, dense air descends down these elevated ice sheets, and it just blows like you wouldn't believe. Now, this phenomenon, we talk about fall winds, is going to be caused by temperature difference or differential between the plateau or the glacier and the surrounding air. So here's an example of how this type of fall wind would develop, this cold and dense, like a katabatic wind. Let's say we have winter snow that accumulates on an elevated plateau. Air above that snow is going to become very cold. You're going to get a shallow dome of high pressure that's going to form near the surface due to that colder underlying snow. And then the cold air is going to descend that plateau and really begin to warm adiabatically as it runs down slope. But even though it's warming adiabatically as it comes down, it's still much colder than the air at the base of that plateau. So regardless, you're going to have a colder wind hitting that area below. So this is generally just an example of how a fall wind would develop, a severe downslope windstorm. Another example of a downslope windstorm would be a Chinook. Now, for those of you watching this video from the Rocky Mountain areas, you're probably pretty familiar with a Chinook. You definitely know what this is. It's literal translation of this is snow eater. It's a very warm and dry wind that moves down the eastern slopes of the Rocky Mountains in particular. And it also can occur in other parts of the world. In the Alps, with the Alps mountains, this wind, this warm, dry, descending wind is referred to as a foehn. And in Argentina, this type of wind is known as a zonda. So take a look over here at the graphic on the right. So what we have going on is we have the winds blowing perpendicular to these mountain tops. So for the Rocky Mountains, as an example, let's say we have a very strong westerly wind. The air is going to rise up and then descend rather rapidly on the leeward side of, we'll just use the Rocky Mountains as an example. So very warm and dry, it warms adiabatically as it descends, and dries out. And if you have any kind of snow cover over here on the leeward side of the Rocky Mountains, for example, and you get this warm, dry wind to just move downslope on that leeward side, it quickly evaporates the snow cover. I mean, literally. This snow cover disappears rather abruptly. You'll notice also when you get sometimes these downsloping winds on the lee side of the Rockies, you can get the development of an area of low pressure, generally to the east of those particular mountains. That is referred to as lee side cyclogenesis. Right, with Chinook winds, continuing our discussion on the Chinook, the conditions necessary for formation, I kind of hit that on the previous slide with the diagram, but we'll cover it another time here just for review. We have warmer air advection, so flow of air from a warmer source or location to a colder one on the windward side of the mountain range. Okay, so you get warmer air coming in. That wind is perpendicular to the windward side of the mountains. You have a stable layer near the mountain peak, and the wind must then blow perpendicular to the mountains on the windward side. I kind of covered that already. Let me draw this out while I'm thinking about it here. Okay, so let's just say that this is the Rocky Mountains right here, okay? So the first criteria, let's examine these again. Warm air advection, flow of air from a warmer location to a colder one on the windward side of the mountain range. So we have, I'll just make a W here for warmer temperatures, okay? Now, let's say that these winds are blowing perpendicular or at 90-degree angle to the windward side of the mountain here, the Rockies. Let's just say this is the Rockies. All right, so the air cannot go through the mountain. It's got to go up. The air rises. And now let's say up here above the mountain peak, we have an area that is stable. So I'll put the letter S to represent a stable atmospheric layer. So as this air runs up against the windward side of the mountain, the wind blowing perpendicular to the windward side of the mountain, that air then ascends, and the air runs into the stable layer. So it's not going to be able to ascend or rise any further. Instead, it gets shoved right back down the lee side of this mountain, and that results in the Chinook wind. And again, it's known as a snow eater. The Native Americans use that term. So if you have a lot of snow over here on the leeward side, the east side of the Rocky Mountains, let's say, and you get the Chinook wind, it's going to quickly, like I said, that snow is going to quickly disappear. All right, so again, just wanted to really hash that out with another diagram to really bring the point home. Now, with Chinook winds, you got strong winds. They're flowing perpendicular to the mountains. We already talked about that here. They produce a trough of low pressure over here on the lee side now that tends to force the air down slope. So in addition, we kind of saw this in the last slide, sometimes you get that low pressure develop in the lee of the Rockies. That's called lee side cyclogenesis, or low pressure development. It's going to help to pull that warm, dry wind, that warm, dry air. It's going to help accelerate it even further. I mean, these winds get really strong, specifically in the wintertime. And as the air descends, just a reminder, it's going to warm adiabatically. Please refer back to my video, my past video in the training series when I talk about adiabatic cooling and adiabatic warming. You can have, because of this accelerated warm, dry wind going down slope, you can get some crazy temperature rises. They could be as much as 59 degrees Fahrenheit, a rise in temperature at 59 degrees Fahrenheit in less than 1 hour. Just impressive stuff. So with downslope, for the downslope windstorm types, the Chinook wind again, you also have a Chinook type wind that forms in Southern California, and that is the Santa Ana wind. This is found in the Southern California area, like I mentioned. It's a very hot and dry wind. It greatly increases the fire threat in the area because it's descending some of the Santa Ana mountains in Southern California, and when it's really strong, it descends those Santa Ana mountains. A very warm and dry wind. It basically pushes the low clouds of the marine layer well out to the Pacific Ocean, well out to sea. So you get a lot of clear weather with this type of situation. But unfortunately, that land is so dry already, and then you add warm and dry air down that lee side of the Santa Ana mountains, and you can really have some fire danger in a short order. And then when a wildfire breaks out with these strong Santa Ana winds, I tell you what, that can spread rather quickly. Those fires, those wildfires. So I recall living through the situation here in California, and these usually develop in the fall. So I would say October is like one of the peak months that you're going to see Santa Ana winds in Southern California. Another type of downslope windstorm event is known as a bora. Now these are cold downslope winds. So this is not like the Santa Ana. Santa Ana's warm downslope wind. This is a cold downslope wind. Conditions necessary for the formation of a bora. Now we get colder air infection. We got colder air coming in on the windward side of the mountain. We still have that stable layer near the mountain peaks. And we still have the perpendicular wind component. So with a bora, a cold downslope wind, we just have colder air moving in on the windward side of the mountain. Everything else pretty much remains the same. And as cold, dense air descends the mountains, it's going to warm by compression. We have the adiabatic warming, but it's still going to be colder than the surrounding air at the base. And the pressure rises are going to be common on the lee, in the lee of the mountains. So this bora wind is very similar to the first wind we talked about, this katabatic wind. Okay, so it's going to be very similar to that. So now now that we've got through the windstorm events, the downslope windstorm events, let's talk about heavy rain events now. This affects many of us living in the United States as well as Europe, anywhere in the mid latitudes really. When we have heavy rain, what is the criteria for heavy rain? What does the National Weather Service use for criteria? Generally, this is what we get. It's an accumulation of at least 6 inches of rain in just 12 hours or less time. That's considered heavy rain. The favorable conditions for heavy rain: stationary or slow-moving thunderstorms. When you get the weak steering currents, those weak upper-level winds, the storms simply just don't move very fast. This is quite common in the summer season because your stronger winds are generally further north, associated with the jet stream up towards the U.S.-Canadian border. So you can get stationary storms that just keep dumping heavy rain for an extended period of time, or even just slow-moving thunderstorms. You can also get thunderstorms that move over the same area, and this is known as a training effect, similar to a train going down a track. All right, so you get these thunderstorms that just a line of storms just keeps firing up over the same area and just keeps moving over that same area. You can result in some heavy, heavy rain. These mesoscale convective complexes, they're abbreviated MCCs. These are thunderstorms which are a special type. They cover a very large area. Okay, so these MCCs, being in the Midwest when I was younger, I could tell you right now, I've seen one of these MCCs blow up right over my location. Common areas that get MCCs is Iowa, Illinois, Indiana in the summer. And the strange thing about these, and I won't go too in depth on this and get off track, but these form at nighttime and they maintain the instability throughout the night. Most thunderstorms will die off or dissipate after sunset. When the source of the sun is lost, you lose that source of heating after sunset. Not mesoscale convective complexes. So I've seen these happen at night, and they do dump heavy, heavy rain. Additionally, with heavy rain, you can get strong moist winds, overrunning a stationary or warm front, that overrunning process, and then tropical cyclones. We know this all too well. If you live anywhere from Texas to Florida along the Gulf Coast, if you live anywhere from Florida up the East Coast, we've seen some prolific rainfall amounts associated with landfalling tropical cyclones. Okay, now let's move to heavy snow events. We're going to switch it to the winter theme here. I just love this picture, guys. I mean, if you're a dog lover, this is just absolutely hilarious. I mean, you see this dog. This is a lot of snow. You see the leash here, the red leash the owner's got on the dog. But I mean, this dog has popped his head up in the snow. That's a considerable amount of snow. All right, so heavy snow events. Now, the thing with these is it's going to be dependent on location. And as an example, if you live in North Dakota, you've got a lot of heavy equipment, heavy snow removal equipment. I mean, you can get a foot of snow and you're probably laughing in North Dakota. All right. But if you get any kind of snow in a place like Mississippi that just doesn't get it and has no snow removal equipment, 1 inch to 2 inches of snow in Mississippi is a huge deal. North Dakota, you'd be laughing at that for sure. So, it just depends on snow removal equipment. What do you consider heavy snow? Different areas have different criteria, and the National Weather Service offices will issue these winter storm watches and warnings, heavy snow warnings, based on that geography. All right, heavy snow occurs, this is the official definition, when you get 4 inches or more that falls in a 12-hour period or less, or you get 6 inches or more of snow that falls in 24 hours or less. Common condition associated with heavy snow. Unfortunately, one of the more difficult driving conditions to deal with is blowing snow. Again, I grew up in the Midwest, and when you just got these flat open fields, these flat open cornfields, all right, and you get the snow to fall, and you get like the really strong northerly and northwest winds, this really can reduce your visibility over the road. I mean, it can almost result in ground blizzard impacts. I've seen it that bad. It can severely limit your visibility. It can cause large snow drifts. I remember driving in December one time around the holiday back in the Midwest, and literally the snow, it was blowing across the road so bad, you couldn't even see where the road was. Now that's scary. All right, so what are the situations synoptically that produce heavy snow events? All right, so first let's talk about a non-occluding low. Okay. The heaviest snow is going to occur to the left of the low pressure track in relation to the low pressure direction of movement. So look over here on the graphic on the right. You're generally going to have the heaviest snow to the north, and then also it's going to extend back here to the northwest a little bit. All right, so this is the direction. This is your L for low pressure. This is your lowest barometric pressure. Here's your cold front. Here's your warm front. And then you see this is an overrunning situation. North of the warm front, we have a band of heavy snow due to the overrunning. But you can also get it in addition to the north of the low, also back here to the northwest. The snowfall rate is usually more than 1 inch per hour, and this can last for 4 to 8 hours. This is with a non-occluding low. So we don't have an occluded front here just yet. This system hasn't occluded out yet. It's still deepening or getting more intense at this stage. Now, with an occluding low, all right, where we get an occluded front, remember I mentioned in the training on fronts, weather fronts, talked about a cold front. It's colder, denser air catches up to the warm front and lifts that warm air off the ground. That's an occluded low. Occluded lows generally are associated with more mature mid-latitude cyclones. This is generally where low pressure reaches its lowest barometric pressure, and the storm is at its most intense stage, in the mature stage, when the low is occluding. Heaviest snow with an occluding low occurs to the left of the low pressure track in relation to its direction of movement. And it's notorious for dumping just large amounts of snow. Look at this graphic here in the bottom left. All right, so this arrow, black arrow ahead of this cold front here, represents a surface low pressure movement. So it's going to the northeast. We have the occluded front. Let me go and get my drawing utensil out here to kind of circle it. This is our occluded front right here. All right. So the occluded front is there. Our low pressure is back here in the colder air. And look at where our maximum snowfall area is here in this green oval shape. This is where you're going to get your heaviest snowfall rates. And this is why it's so very important as a meteorologist, when you see them do the forecast in the winter, this is really not an easy forecast, because you really have to know where this low pressure system is moving to determine who's going to get the heaviest snow. And just a slight shift in the low pressure system track can make all the difference in the world between 1 inch of snow to a foot of snow. I mean, really it can. So this is where it gets really tricky as a forecaster in the winter season. Now, heavy snow events also are associated with these strong low pressure systems. These occluded lows can also lead to blizzard conditions. I got the criteria for a blizzard here listed. Blizzard conditions, this is courtesy of NOAA. The sustained winds must be 35 miles per hour or more. Strong winds will reduce the visibility to less than 1/4 of a mile for an extended period of time. And this 1/4 of a mile restriction of visibility has to be for at least 3 hours. That's the extended period of time criteria. The temperatures are usually less than or equal to 20 degrees Fahrenheit. So just very, very cold, very windy, blowing the snow all over the place. You know, you have the falling snow, you have the blowing snow, your visibility is reduced to less than a quarter of a mile for at least 3 hours, and that's a blizzard. Moving on now to freezing precipitation events. These are very dangerous to drive on. You know, freezing rain creates a very beautiful winter wonderland by coating everything with glistening ice. I've seen tree branches coated before. I've seen, unfortunately, power lines coated. And in some cases, you get thick enough ice on power lines, it's going to snap those power lines. And a lot of folks, unfortunately, are going to lose power. But highways, very dangerous to drive on freezing rain. These highways can turn into basically ice rinks, and entire airports and communities just become crippled. There's a shutdown, a complete shutdown. I lived through 2 major ice storms in Tennessee. And I'll tell you, it was January of '94. I kid you not. They were a week apart, the ice storms. And it was insane how much they shut everything down. You could hardly walk. You know, you're slipping and sliding all over the place. Cars trying to drive in it, slipping and sliding. This leads to a lot of accidents. And yeah, the power went out temporarily. And this was a bad ice storm around the Memphis area. And if you look up January '94 ice storm for Memphis, I lived through that one. And yeah, that was an incredible thing to see. Now, one thing to keep in mind is freezing rain is common ahead of a warm front, moving into a colder region. So it's an overrunning situation again. You still have that cold sub-freezing air at the surface. I'm going to go over here to the right and show you that. So you see the 0 line here. Let me go ahead and draw it out here. I'll get your attention on each of these major pieces of this. Okay. So you notice this. Let me find my cursor. Okay, there you are. This 0 degrees Celsius is the freezing point of water. And you notice it's this line right here. It's this horizontal little dashed black line. So if you have any precipitation, what's going to happen here? Let's just follow the precip from the base of this cloud. So you have this cloud right here, right? You got this cloud. It's below freezing temperatures, okay? So it starts to snow. As the snow falls into a warmer layer, this is a warm elevated layer here, and it's about 1,200 feet thick. See this? Right, so as that frozen snow falls into this above freezing, this elevated warm layer, temperatures above freezing, 1,200 feet of above freezing temperatures, the snow's going to completely melt. Okay? And then if, let's say this is turned into sleet, see these circles here that represent sleet, let's say that sleet then descends in a 700 foot above freezing layer. Or actually, no, this is a below freezing layer. I apologize. Yeah, so we have a shallow below freezing layer, 700 feet thick towards all the way to the ground. That sleet eventually is going to partially melt and become freezing rain. If the surface is 32 degrees or less, that rain is going to freeze upon immediate impact. So you really have to look at the vertical temperature profile. Again, this is not easy. Winter forecasting is not an easy thing. Storm track is so critical, as I mentioned, about where the heaviest snow is going to fall, generally to the northwest of the low track. In addition, you got to figure out, okay, what is my temperature profile in the vertical? How thick is my warm layer, my elevated warm layer? Okay, and forecasters have special rules of thumb to determine, how thick the warm layer, the above freezing layer air is aloft, whether you're going to get freezing rain, whether you're going to get sleet, whether you get a mixture. So this is not easy, okay? This is a very difficult process to forecast for. Now, freezing rain initially starts as a snowflake in the cloud. We see that here, right? Snowflake in the cloud. You're below freezing initially. The snowflake descends towards the ground. It falls in that warmer air. It begins to melt right here, this 1,200 foot thick above freezing layer. If this melting snowflake falls through a sub or below freezing layer of air, it will begin to freeze again, and that's the ice pellets I was showing you right here, these little balls. All right. If the precip falls into a shallow cold layer near the surface where it's below freezing again, it reaches a surface as these super cooled liquid droplets known as freezing rain right here. And freezing rain is common ahead of a warm front, moving into a colder region. Again, you got warm, moist air overrunning colder, denser air at the surface, and that's the perfect recipe for freezing rain. Now let's move on and talk about icing. Now, we talk about icing and turbulence. We're really most concerned about aviation. You might wonder one time when you're going to the airport and, you're trying to figure out why there's a delay in your flight. Well, a good reason for those delays could very well be icing, specifically in wintertime when your freezing level is much lower and closer to the ground, especially when you get a really cold air mass to move in. Your freezing level could be at 3,000 feet, for example, and anything above that's below freezing, and icing could be a concern. You may have also sat in a plane before you started taxiing to the runway, and you may have noticed them spraying the plane down, and they're basically trying to de-ice the wings and the main body of the plane. I started my work as air traffic controller, so I understood the real importance of weather when it came to flight, and for pilots to safely get from point A to point B as an air traffic controller. Weather was a very important consideration to make, and icing was one of those things that we learned as air traffic controllers. Now, the FAA, the Federal Aviation Administration, by the way, estimates that 50% of all aircraft accidents are weather related. Can you believe that? 50%. Three major flight hazards. In addition to the turbulence, which we'll get to that, we're going to start with icing first. In addition to icing and turbulence, we also have visibility obstructions, such as a dense blanket of fog at an airport. This is really what icing can do to a plane. It can decrease an aircraft's ability in many ways by adding increased aircraft weight. You obstruct the airflow that normally is supposed to flow over the airfoils, over the wings. Icing lessens the intake of air needed for the engines to properly perform. And when we talk about the synoptic setup or situation for icing, it's common behind cold fronts because you have that colder air moving in behind cold fronts, and your freezing level is getting lower, closer to the ground. Ahead of the warm fronts on the cold side, because you're in that colder air on the cold side of the warm front, you're in that colder air. Freezing levels will be lower there. And when you're in clouds with cold air advection, so if the plane's flying through a cloud and there's colder air moving in at the same time, that's a recipe for ice, as well as freezing precipitation events. Here are the icing types we'll discuss. We've got rime icing, clear icing, frost, as well as mixing icing. For rime ice, this occurs when an aircraft flies through a cloud, and this cloud is made up of tiny water droplets. And when I think of tiny water droplets in a cloud, I'm automatically thinking of stratus type clouds. These small cloud droplets hit the wing as that plane flies through the cloud. They freeze immediately before having time to spread out. So it's like instant freezing on the wings. And this will leave an uneven, brittle coating of ice on the leading edges of the aircraft, which again is going to add weight. It's going to increase the drag of the aircraft, and it's really going to hinder the engine's performance. Now, what does rime ice look like? It looks white in appearance because these small droplets trap air between them. It's not as severe as clear ice. We'll talk about clear ice here in a moment. But rime ice is not as severe as clear ice due to weight differences between the two. Rime icing is normally found in stratiform clouds. I mentioned it, smaller water droplets. You're going to have less vertical motion in a stratiform cloud. You're going to have smaller water droplets in those stratus clouds. And we generally look for icing conditions in clouds with temperatures from 0 degrees Celsius to negative 22 degrees Celsius. But you also can get some rime icing mixed with clear icing in cumulus clouds, depending on where you're at in relation to the freezing level. But you see here, cumulus clouds, the temps range from negative 15 to negative 22 Celsius. But really, rime icing is a stratus type cloud predominantly. Again, you can get mixed icing, both clear and rime, in cumulus clouds, depending on the vertical growth of that cloud. For clear icing, I want you to imagine an aircraft flying through an area of freezing rain. As these large supercooled droplets strike that leading edge of the wing, they spread out and form a glaze. So we're talking a glaze or a film of water that slowly freezes to form a solid sheet of ice. That's clear ice. It's very difficult to remove with de-icing equipment. Clear icing is usually associated more with those larger water droplets in cumulus clouds, generally looking for temperatures in the cloud ranging from 0 degrees Celsius to -8 degrees Celsius. And the most severe cases of clear icing generally are going to occur in developing thunderstorms. For frost, this is a common one that we see, specifically in the fall season. You might wake up one morning and find these feathery patterns on your windshield. Or you might see it on your windows itself of your house. You might see it on the grass blades. This is a light feathery deposit of ice crystals that can form on parked or in-flight aircraft. So frost can also be a form of icing for aircraft. For mixing ice type, we have a combination of both clear and rime icing. And this mixing or mixed ice type is going to occur with temperatures between -9 degrees Celsius and -15 degrees Celsius in those unstable clouds. Now, unstable, I'm already thinking of cumulus clouds, those cotton ball type clouds. For icing intensities, how are the intensities classified? We have trace icing, we have light icing, moderate icing, and severe icing. For trace icing, the accumulation rate is not really going to be significant unless it's encountered for over 1 hour, so it takes quite a bit of time for trace icing to be a problem. De-icing equipment is not used in this case because it's, like I said, just a trace, accumulation rate not significant. For light icing, now this may create a hazard in flight if it is in this icing environment for over an hour. Occasional use of de-icing equipment prevents buildup of it, so this is where you kind of use that de-icing equipment occasionally. For moderate icing, this is a case where the rate of accumulation is such that even short encounters become hazardous to an aircraft. Continuous de-icing or changing course is necessary in this case. So pilots are flying, through the clouds. They're going to notice some of this stuff, be using their de-icing, and they may need to change their course slightly to get out of these clouds if there's icing, moderate icing present. And then with severe icing, even continuous de-icing fails. This is the worst case scenario you want to be in if you're a pilot flying through clouds. Immediate diversion from the icing area is necessary. It's most common with clear icing. Now let's talk about turbulence. Has anybody watching this video ever encountered a time where you were sitting in your airplane, you're flying at the flight altitude, let's say 37,000 feet. Everything's cool, but all of a sudden the plane just starts shaking all of a sudden starts shaking really bad. This is a case of turbulence. It's caused by these irregular motions of the air, such as eddies or gusts. And it can cause structural damage to aircraft and injure passengers. And we've seen this plenty of times with turbulence. There's some cases where planes will be airborne, they'll encounter some significant turbulence and they have to turn around and land right away, make an emergency landing because of damage to the plane. There are three main types of turbulence that we're interested in. There's thermal turbulence, mechanical turbulence, and clear air turbulence. So let's break these down. Thermal turbulence is commonly classified as convective in nature. It's a result of the sun heating the Earth's surface. It creates these swirls or eddies in the atmosphere. Most thermal turbulence is going to be light, but it can be moderate over uneven mountainous terrain when it's hot. So this diagram on the right is showing you these convective air currents that are setting up. I don't have a sun icon out in this picture, but I should. So just imagine that the sun is out, it's daytime, and the sun is intensely heating this uneven terrain. You notice how this terrain is not completely flat or smooth, it's kind of bumpy, right? Different elevations of these mountain peaks. And you're going to get a lot of turbulent airflow as the slopes are heated up by the sun. Air is going to rise, but you're also kind of seeing some of these eddies. And if you're a plane flying through any of these eddies, you're going to experience that thermal turbulence. Mechanical turbulence, on the other hand, in the lower levels, you get mechanical turbulence, which is directly related to the roughness of the Earth's surface and stability of the atmosphere. So the rougher the terrain, let's just say it's more mountainous, as well as a day in which we have a lot of instability, that's going to give you your worst cases of mechanical turbulence. So when wind flows or blows over this uneven terrain, it's going to create these eddies. We kind of already talked about that right here, right? These little swirls. These eddies form on the lee side of terrain obstructions or objects. Again, the stronger the wind speed, the greater the chances for increased severity. With mechanical turbulence, the unstable atmosphere increases the severity of the eddies, but over a shorter duration. But that's all it takes. You know, if you're flying in an airplane, it doesn't take much to really move a plane around with the turbulence. And it might be short duration, but you're still going to feel the effects of that turbulence sitting in that plane. Stable atmospheres promote longer duration turbulence, by the way, but the severity of the eddies are going to be less. Additionally, with mechanical turbulence, another example of this is going to be mountain wave turbulence. So some of the mountain wave turbulence requirements are listed here. We have that stable layer at the mountaintops again. I mean, that's a common theme, isn't it? We got stable atmosphere above the mountain peak. We have strong winds. Look at this diagram on the right. We have strong perpendicular winds to the windward side of this mountain. We have upper level cold air advection. Why is that important to create more turbulence? Because when you have a cow situation, we talked about that in my recent training video. Let me do this here. So, what did we say about the cow? Remember? What is cow? That is a cold air mass over a warm air mass. That is going to result in the greatest mechanical turbulence. It really is. So if you get colder air moving in well above the mountain, well up in the atmosphere, above the ground, that is going to help increase the instability. Specifically, if it's during the day, you're going to get these convective currents to set up. If winds are strong enough and a rotor cloud is present, there's extreme turbulence possible. All right, so I'm going to tell you right now, as a former air traffic controller, I cannot get this to work right now, and I apologize. Oh, there you are. Okay. All right, so see this on the lee side of the mountain? You got these strong winds blowing up against the windward side of the mountain. You got a stable layer. I'll represent that with the letter S here. But you have colder air moving in over a heated surface. And then you've got these type of roll clouds, or not roll clouds, roll eddies, which form what's known as rotor clouds. These right here, this big X, is what a pilot wants to stay away from. Those are very, very turbulent. You get extreme type of air turbulence in those. So a lot of times you will not see the pilots go anywhere near these rotor-shaped clouds. They will remain well above those clouds, okay? And there's a good reason for it. I remember when I lived near Mount Etna. I lived near Mount Etna over in Sicily. You would see like the lenticular clouds look like UFOs, the shape, and you'll see rotor clouds on the lee side of Mount Etna in the winter because you get these strong westerly winds blowing up against Mount Etna, that windward side. And yes, no pilot is going to go that direction, believe me. All right, so now let's talk about turbulence type. The next turbulence type we'll talk about, we talked about mechanical turbulence type, we talked about thermal, okay? And now we're going to talk about clear air. Now this one's a very dangerous form of turbulence. Have you ever heard of the acronym CAT? C-A-T. Literally CAT stands for clear air turbulence. It's not associated with any convective clouds. And that's really the problem with it. You can't really visibly see like a rotor cloud or, lenticular clouds. You can't see any kind of cloud that's kind of going to give you a tip as a pilot that there might be turbulence ahead. In this case, this turbulence is not clear air turbulence, not associated with any convective clouds. In fact, clear air turbulence is associated with jet streams, believe it or not. Strong cold air or warm air advection is another cause of clear air turbulence. Upper air closed lows can be a cause of clear air turbulence, and sharp troughs or ridges. But a lot of times they're associated with these jet streams. And a plane will be flying. There's been a lot of reports of this over time. They're flying at cruising altitude, 35 to 40,000 feet. You know, you're up near the jet stream level at that altitude. And all of a sudden you start, you're in the plane and you really start feeling the effects of this turbulence, this clear air turbulence. It has resulted in damage, and it's really hard to depict it. Here are the turbulence intensities now. Let's go over these. We have light turbulence, moderate turbulence, severe turbulence, and extreme turbulence. For light turbulence, this may cause a slight irregular change in the aircraft's altitude. It's kind of small little bumps when you're sitting in the plane, and you feel those small little bumps. You may feel a strain against restraints. Loose objects in the aircraft cabin may move around slightly, but it's not really very noticeable. This is the type of turbulence where you'll be flying, you'll have your eyes closed, you'll be listening to your earbuds, and it's just a slight little bump. Moderate turbulence now, the aircraft does remain in positive control of the pilot, but the occupants do feel a definite strain against their seatbelts. And you will definitely notice or hear objects moving around. Trying to, for example, to get up and go to the bathroom, you're going to really be wobbling your way to the bathroom in this case. Walking about is difficult with moderate turbulence. As far as severe turbulence, this is an even worse case scenario for a pilot. The pilot may temporarily lose control of the aircraft. Occupants are going to be forced violently against their seatbelts in this case. And then finally, extreme turbulence. This is the worst case scenario. It's very rare occurrence, but the aircraft is basically violently thrown about. It's practically impossible to control for the pilot. And this is the case where you get the structural damage. And this is where, in a lot of cases, the plane will make an emergency landing at an airport because of the damage caused by this extreme turbulence. All right, that wraps up the Severe Weather Fundamentals Part 2. All right, so we covered a lot of different topics in this training video, right? We started things off with these downslope windstorm types. We looked at fall winds. Katabatic winds, an example of a fall wind. Cold, dense air moving downslope. Chinook wind is a warm, dry wind moving downslope. Specifically common in winter in on the east side of the Rockies. Effectively removes snow very quickly. The Bora is a cold, dense wind as well. And kind of the causes of what causes these winds. So we did those. We did the Chinook winds again. We kind of went over those, the Bora winds, the cold downslope winds. We then moved into heavy precip events, starting with heavy rain events. Then we did heavy snow events, kind of the synoptic situation where you find the heaviest snow in relation to a non-occluded low pressure as well as an occluded low pressure. And by the way, this is the type of blowing snow you get in the Midwest, guys. This is what I was talking about around the holidays one time. I'm driving in the country, and you couldn't make out the road here because that wind was whipping this dry, powdery snow up so quick you could barely see in front of you. So we talked about the heavy snow events, including blizzard conditions. These are the criteria for the blizzards according to NOAA, and so you'll see blizzard warnings issued for locations that meet these criteria. Freezing rain, freezing drizzle, very dangerous freezing precip event. We talked about how icing can impact aircraft. We talked about the icing types. We covered those in depth. And then we talked about the icing intensities and how those change. And then we talked about turbulence, which many of us have experienced just flying in a plane before, going to visit family or friends. So that's all I got for now, everybody. Certainly hope you're enjoying the training series. We've got some more training ahead. What can I say? I mean, I've got it locked and loaded, guys, for more training ahead, more interesting weather topics. So I certainly hope you enjoy this. My plan is to run the training series out through probably the end of August. So I'll keep the training videos coming. And again, hope you really enjoy the explanations. That's all I got for now, everybody. Take care and God bless everyone.